But here, I have all the combination possible
Yeah.
for the one,
Yeah.
the input 1, and this all the combination possible
Okay.
for the input 2 and 3.
Got it. All right.
So I see the combination. If there are two inputs in one, the output will be 1.
Yes. Okay, I got your point. So now for that KV diagram, it's a correct one, by the way. For that KV diagram, how to build the groups? What you prefer to take into account, the ones or zeros, or how you define the groups?
I will define with the ones because there's a bigger group of ones here. So
Could you please just mark it? It's damn it, that's probably some screenshot, right?
yeah, that's a
Now I
photo
got it.
actually.
All right. What's your intention to take into account the 3 ones, right? Below.
Yes, I will take these 3 and
Okay,
this
if you
only one.
define the group like this, is that a good idea or bad idea?
I think the bigger the group,
That's correct. That's
best.
absolutely correct. But then the problem is amount of ones or zeros should be power of 2. 3 is not power of 2.
Oh, okay, that's true. I forgot that. Well,
So, all right, guys, it's a good approach. It's a good way. The only thing what I'm missing right now, first, I would prefer to see a rough RBD first. We have to deal with the 2 out of 3 system, right? Create first the rough RBD. Then that table of truth, as we see it here, it's absolutely correct. It's fine. And also the KV diagram is fine. The only point is right now it's necessary to build the appropriate groups correctly. Okay?
okay.
So then please just extend your solution. As I said before, I think 15 minutes is more than adequate. So if you be ready with that earlier, then just let me know, okay? And guys, for the rest of you, please don't just wait for a ready solution. Try to elaborate your own, okay?
Teacher.
Yes.
I have a comment regarding the exam.
Yes.
Yes, it's because we were supposed to talk class, but I think that we just finished without talking about it. I talked with most of my classmates here, and we were willing to give an extra 30 minutes to each class and have the exam on Friday. I don't know.
No problem. I would just stick on that solution because we have Friday scheduled. So from that point of view, it should be okay for the rest of you. Otherwise, it's just too much discussion. And again, to tell you the truth, I'm not really happy to have some shifted class on Sunday. Saturday is okay, but Sunday, no, sorry.
Yeah, for me, Friday is perfect as well.
All right, then let us decide just to have some additional, let's say, half an hour in order to compensate the time.
Okay.
So, all right, now, guys, please, yes, do you have any other remarks?
No, that's it. But also I have something about the exercise. Let me just connect my tablet.
Yep. Guys, besides, if I have a pause right now anyway, because Ricardo is just preparing to share the screen. Next week, we'll start the second lesson, digital failure diagnosis. Who from that class is assigned to the second lesson for the digital failure diagnosis, please raise your hand. Just use that function, raise the hand, and I will see immediately who will participate. Oh, that's brilliant. Okay. Okay, 7 of you, right? Brilliant. Because as I said before, we will use some knowledge from that class in the second one. And right now in my participant, I have, I think, 10 persons, which would be a bit strange, because if they don't have the necessary, knowledges from the first one, that would be quite heavy. But let's see what happened. All right, good, understood. So now let's take a look.
Yes.
This is your table of truth. I assume it's the same like we saw it before, right?
Yes, it's the same. And this is my KV diagram.
Okay, and now you define the KV diagram and you define the groups. Yes, absolutely correct. Absolutely correct. Then you also operated over zeros to define the CNF. Okay, I got your point.
Yes,
that's a brilliant solution.
I just had a question because I forgot when I was doing it first. I forgot why was the reason that instead of having here, like, let me just put it in red, 1 0 and here 1 1, we put it like that. I forgot the reason.
First, it would be enough just to read the script.
Okay.
Because it's described there. And the second question, or better said, second answer is quite simple. What we are using here is so-called gray code. So that means if you have more than 2 variables, because actually it's a typical trap, and therefore I was surprised to see that first solution. It's quite surprising, but it was okay. And now you just confirmed that. Actually, I had a hope that you read the script, but obviously you doesn't. So again, here the situation is quite simple. When we are working with KV diagrams, the art to work with appropriate KV diagrams is how to scroll them. So that means how to build the groups. That's all about that. And for that purpose, when amount of the variables and more than 2, as we have it here, then the appropriate combinations, the appropriate binary combinations should be written in this way as you have it right now. So positions has changed from 0, 1 to 1, 1. How many?
2, well, 1, 1, 1, 1.
Just one position, right? When we will jump from 1, 1 to 1, 0.
Also 1.
And now even better, if we will jump from 0, 0 to 1, 0, how many?
1.
This is exactly the reason why.
Okay.
Because otherwise we will get a change from 0, 0 to 1, 1, change of 2 binary positions, right? This is that is an issue. And if you would combine now the table of truth, better say the KV diagram, using that, we will make intentionally that error. Yep, 1, 0 and 1, 1. So here 0, 1, as you had it previously. So 0 and here 1, okay. Should be 1, 1, 1. Yes. So now try to build groups.
For the first one, it would be, oh wait. This one, it's C and A and C. No.
All right, for the red one, take a look. A is equal 1. B changes the value and C changes the value, right? Why that? I'm confused right now. Again, for the red one, take a look. What I have inside of the red group? B is 0 or 1. C is 1 or 0. So that means they change the value. It should be just A. You agree with me or not?
The one that changed the value, it's B and C, right? Oh yes, that should be okay.
Now you see it, right?
And here, the one that changes the value, then it would be B and C.
So this is B and C, but we're also missing the third term because you can make some, I don't know, green group, unifying the ones inside of 1, 0 and 1, 1. Exactly this way. So what will happen in this case? A is constant, B is constant, but C changes the value, right? So it would be AC. So now, now compare that result with the correct result on the left side. Obviously, that's an issue, right?
No. Yes.
The first term is wrong. And this is the reason why. Because again, here, the sequence of the appropriate columns does matter. And again, guys, please read the script because that situation is described inside of the script. Yes, absolutely. So, all right, the only thing which is missing right now in your solution, could you please provide the appropriate rough RBD?
B and C. Let me just, because I don't remember.
Well, you can obtain that logic immediately. So the structure of the RBD you can obtain immediately from the appropriate logical expressions.
Yeah, but this one is like,
Especially,
I don't remember the symbol. Is this one or yes? Right?
Hold on. I'm asking for just reliability block diagram, the rough one. For 2 out of 3.
Well, the relevant would be like, well, A, B, and C, and we had them like this, and it was.
No. I need an RBD without any modifiers. I need that canonical form of RBD, which is nothing else but AB, AC, BC in parallel to each other. We need to take into combine the blocks. Write the block A. Just make a frame around, yes, and now connect it to the right. Make the second block and write B. Because you call the elements A, B, and C. So now in the second row, write A and connect it to C. Exactly. Now you got my idea, I think.
Yeah.
So, and finally, no, it should be CB, not AB.
CB?
CB, because we have AB, AC, CB, or BC, it doesn't matter. So and now connect all of the 3 lines.
I was thinking like A, B, C, and then again A.
And then remove the diagonal.
Yeah.
Yes, okay, do it, just continue.
Okay.
No, come on, man, just do it, yes. So A, B, C, and again, and now remove diagonal, what you'll get.
Yes, the combination.
You have that BC, you have AC, you have AB, right?
Yes.
All right. So now take a look on that rough RBD, and now please take a look on your logical expression in D and F form.
In D and what? Sorry?
D and F. You define two
Oh,
logical
yes.
expressions, one
Yes.
DNF, one
Yes.
CNF. Now take a look on the DNF. What you can recognize here, it's nothing else but the structure of the appropriate rough RBD. Take a look. You have BC line, or you have AC line, or you have AB line. Can you recognize it?
Yes.
This is exactly the structure of your RBD. Okay, you got my point?
Yes.
This is the reason why a DNF form is preferable one. It could be understood just, you know, with that from the visual point of view. It's much more better readable. But now compare it with a CNF. Actually, this is one and the same function. But now to understand how that CNF should be reflected by means of the RBD, damn it, it's challenging.
Yes.
So again, this is the reason why I said, and I can just repeat, don't be confused. One and the same function could be expressed in many ways. In some of the cases, a DNF is, I would say in almost all of the cases, a DNF is preferable one because it's easier to understand. It's better readable. But in some of the cases, the CNF would be most preferable because if you have, let's say, less zeros than ones, then obviously it makes sense to create the CNF. Especially because if you want, you can easily then convert CNF to DNF. If you would now open the brackets inside of CNF formula, you should get exactly the DNF expression. Okay, you got my point.
Yes. But wouldn't it take like way to simplify it?
Well, you wouldn't simplify it because what you have right now in CNF form is minimal and necessary expression. Could not be simplified anymore. But you can convert it to DNF by opening the brackets and doing some, you know, formal transformations,
Okay.
Boolean
Yeah.
transformations. As a result, you will get just a DNF form. You can trust me by word right now. So, all right, guys. Actually, the task is solved. And now, seriously, to the rest of the class, guys, please. You should elaborate your own solution. Of course, it would be not possible that everyone present that solution and we discuss the appropriate solutions of every one of you. But nevertheless, please, more activities. We have to accelerate because we have a huge amount of materials in front of us, and believe it or not, it's actually last week of that course, Friday exam. From that point of view, the time is running. All right. Any questions about that exercise? Was it clear enough?
Yes, Professor. That's clear.
Same result except for the CNF. I didn't do that, and I do not.
You mean now it makes sense to Ricardo? Could you please reshare your screen again?
Yes. Let me.
Fernando, if I understood correctly, you are asking to explanation how to get the CNF, right? Is
Yes.
that correct?
Yes.
Okay, then let me just briefly explain. Take a look. Here we should take into account the, let's say, the KV diagram below. So the first one, the upper one, it's we are operating over ones, and the lower one we are operating inside of the same KV diagram. It's still the same KV diagram, but now we are operating over zeros. Okay, so also here we've defined 3 groups. And you remember I said the art, how to use the KV diagrams is all about how to scroll. Because what I assume you're confused why 0, 0 is combined with 1, 0, right?
No, I understand that bit.
Okay.
Not how to get the equation.
Okay, so now we defined 3 groups of zeros. Okay, so
Yes.
now let us consider, by example, the group 0, 0, 0, 1. So in this case, we have A constant 0, B constant 0, and C changed the value from 0 to 1. You see that?
Yes.
So then obviously that term, the first group, that red group, is independent from the variable C. That means we know if we're about to create CNF, we will get exactly the same amount of groups as we have amount of groups inside of the KV diagram. So in that case, 3. Inside of the groups, the variables are connected to each other by means of OR gate, and the groups are connected to each other by means of AND gate. So, and the last condition is inside of the group, if the variable, the value of the variable is 0, then the variable should be taken directly into account, otherwise negated.
Okay.
All right. Any other
Yes.
questions?
No, thank you.
Guys, por favor, read the script. It's necessary because all of that stuff is described there, okay? Just refer to the script, the appropriate chapter. All right, so now let me share my screen because we have to continue. That was our last exercise. I hope you see the slides right now in presentation mode. Is that the case?
Yeah, we can see.
Okay. All right, this is what we discussed, how to create the KV diagram. Now, much more important is that connection, and actually that was the reason for the exercise, because we have to understand how to go from the RBD, reliability block diagram, what was the result from the previous classes, how to describe the appropriate logic, the survival logic, how the system works, which is reflected by the appropriate RBD structure, how to describe it in some formal way. So for that purpose, we need the logical expressions. Now, take a look. Here, we have to deal with a different, and normally, if you're working as reliability engineer, you will always see some typical structures. Serial structures, parallel structures, and let's say that complicated structures which reflects the redundancy n out of k, what we saw also in the previous classes. Now, take a look. If I have to deal with some trivial serial structure like that one, so that means the entire system consists of 2 subsystems, S1, S2, then the appropriate survival logic here, I will switch to a pen. So here, R function, it's always survival logic. Now, that means, by means of that expression here, I can define the appropriate survival logic. The entire system is operational only if S1 is operational and S2 is operational. And here I have the appropriate failure logic. The entire system will fail if S1 is failed, and because of that negation, or S2 is failed. So later in our course, I would prefer to see the expression like this: S1 failed or S2 failed. Okay, just in order to, let's say, save our time. Is that clear so far? Of course, that principle could be extended if you have more than just 2 components inside of the chain. Just imagine the serial structure is nothing else but a chain of the components. It doesn't matter at which of the positions some cell is broken, the entire chain is lost. Okay, this is the reason why. From that point of view, if I have more components which are serially organized to each other, then the appropriate survival function is still a big AND gate over all of the subsystems, okay? Until Sn. And the same story, the entire system will fail if at least one of the appropriate subsystems, by example S1, or etc., 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 or Sn is failed. Again, serial structure is nothing else but a chain of the component. If I have to deal with a parallel structure, as presented here in that trivial case, if I have just two subsystems, S1, S2, which are redundant to each other, and because of that, the appropriate RBD is nothing else but a parallel structure, then, guys, and please keep it in mind, for parallel structures, we have to start first with the appropriate failure logic. Because the failure logic could be expressed in unambiguous and much more simpler way. The entire system will fail only if S1 is failed and S2 is failed. Do you agree with me?
Yes.
Now, take a look, please, on that horrible expression here. I saw that situation many times in which, and this is an absolute disaster, because take a look, what is about here, what we're trying here to describe? We are trying to describe the survival logic of that system, right? And now, I saw many times that the people were just trying to construct all of the possible successful combinations of the failed and intact component. By example, the entire system will be okay if S1 is okay and S2 is okay. That's true, right? Or if S2 is failed and S1 is operational. That's true as well. Or finally, S1 has failed, but S2 is operational. It's everything right. But what do you think? Can we express that survival logic in much more shorter way? Is that possible?
Yes.
What would be the expression?
Just give me a second.
All right, just in order to save our time, take a look. This is the reason why I said, please start with a failure logic first. So here I have my expression. So S1 failed and S2 failed, right? I just rewritten that one. So now, as a consequence, survival logic is nothing else but negation of the failure logic. You agree with me? If I would negate the failure logic, I will get survival logic, quite obvious. So from that point of view, what do I have? I have to negate the expression for failure logic, which is S1 failed and S2 failed, should be negated totally. And now think about the previous class. We discussed the De Morgan transformation rules, right? So this is nothing else but S1 or S2. So that means right now, just compare that expression here and that expression here. If you would, and later on we will start talking about it, about the structures for the survival and failure tree, one thing to implement the appropriate tree structure for that expression, and absolutely another thing to implement the same structure for the same function, actually, for that one. It's unnecessarily complicated. You got my point?
Yes.
So again, I can just repeat. In order to avoid the situations like this, if you have to deal with the parallel structures, then please always start with the appropriate expression for failure function first. And then you can easily get the appropriate expression for survival. All right, and this is what I'm talking about. We've got that proof, or if you want, you can prove it easily by the appropriate table of truth. We've got that situation here. So you can express the survival function either on this way or on this way. So actually you can tell me, all right, this is not a big deal, but it is. Because if you will try later on to implement that expression here in the appropriate industrial CPU or in some electronic circuit or whatever it is, you will get that construction here. And now compare it with that construction here. It's just one DEM operation here. That's it. From that point of view, your CPU load or complexity of the appropriate electrical circuits or PLA or whatever you will use to implement that function, it's significantly lower. And because of that, you will increase the performance of your CPU, you will improve your system if you go this way, that rational way. This is the reason why all of the appropriate logical expressions should be minimal and necessary. And this is the reason why we are practicing how to use the KV diagrams. You got it?
Yes.
All right, then let us continue. And right now we will talk about a very interesting technique just in order to minimize that effort, how to construct the logical expressions. Now, take a look. What you see in front of you right now, there is some, let's say, structure. Consists of the 5 elements, right? You see it, 5 blocks. Some bridge structure. Now, if I would ask you to provide, let's say, the appropriate logical expressions for failure and survival function, what will be your approach? Think simple, think faster. Just what's the first idea? How you would proceed?
I think it will be the sum of different structures.
Too complicated. What I would do at that position, and later on in digital failure diagnosis, I will show you the way how to make it. What I will do, I will just generate the appropriate table of truth. That's it. I will consider 5 elements. With the 5 elements, you can imagine it's quite compact table of truth. Just 2 to the power of 5. It's nothing special. The structure of the KV diagram would be a bit more complicated. And again, to tell you the truth, that, let's say, the biggest amount of the variables that could be handled by a normal human understanding without using some specific software or algorithms is limited by 5. In just some ultra cases, maybe 6, but not more. If you have more complicated functions, then the appropriate structure of the KV diagrams would be much more complexer. But nevertheless, with the 5, we are absolutely okay. So from that point of view, I will just generate the table of truth. I will create the appropriate KV diagram, and I will get minimal and necessary logical expressions. But there is another way. And what I'm talking about is minimal cut set. So that means I would define a minimal and necessary combination of the failed components which will lead to the failure of the entire system. Okay, you got it. So let me just number it. Component number 1, number 2, 3, 4, and 5. So in this case, I can easily say the first minimal cut set is nothing else but the combination of the component number 1 is failed and component number 2 is failed. Don't be confused by that expression here. Originally, that slide was created for the German version, and A at the beginning means Ausfall, so that means failure of the component, okay? So again, if I have the combination of component number 1 is failed and component number 2 is failed, then I will get interruption here and here. And obviously the signal cannot, if I apply some signal on the left side, then the signal would not reach the right side. Because of that, obviously the entire system is failed. The same story here. This is actually nothing else. The second minimal cut set is nothing else but failure of the component number 1 and 3 and 5. Take a look. If I have the cut like this, then the same story, signal from the left cannot reach the right. Next one, the next minimal cut set is again just a combination of the failed component. 2 is failed and 3 is failed and 4 is failed. So we have the situation like this. And finally, if component number 4 failed and number 5 failed, interruption here and here, the same story, the entire system is failed. So now, what's the gain? Comparing to that, frontal approach, if I would just take all of the 5 components into account, generate the table of truth, rewrite the table of truth in the appropriate KV diagram, and generate that logic from the KV diagram, the gain is quite obvious. By means of the definition of the minimal cut sets, I can easily express the appropriate failure logic. Just take a look. I'm still in that structure here. And now I'm about to define the failure logic first, because take a look, we have here some parallel structures, right? And because of that, we have to start with the failure logic first. So now, if I'm defined the minimal cut set number 1, number 2, number 3, and number 4, I can easily say, all right, my system will fail if minimal cut set number 1 is happened, or minimal cut set number 2 is happened, or minimal cut set number 3, or minimal cut set number 4. Okay, you got my idea. So that means we express the failure logic by means of the minimal cut sets. Now, I know exactly that behind minimal cut set number 1, what do I have? I have that structure here. Component number 1 is failed and component number 2 is failed. The same story, I can take into account the structure for the minimal cut set number 2. That would be that one. For minimal cut set number 3, this is nothing else but that one. And finally, minimal cut set number 4. This is that combination here. So that means, based on the appropriate definitions of the minimal cut set, I can easily define detailed expression for the failure logic of the survival system. This is nothing else but that expression here. And once I have the logical expression for the failure function, if I would negate it now, I will get the appropriate expression for the survival function. Quite obvious. If I would negate that original expression for the failure function, I will get the entire system will survive if minimal cut set number 1 doesn't appear or not happened, and because of that, negation of the minimal cut set, and minimal cut set number 2 doesn't happen, or and minimal cut set number 3 doesn't happen, and minimal cut set number 4 doesn't happen. So by means of that, I've got minimal and necessary expression for the survival function. The only thing what I have to do right now in order to get detailed expression, I should take that one for the failure function and apply the appropriate De Morgan rules. That's it. Sounds easy, like? So now, let me summarize briefly before we make the next steps. One of the previous results, what we've got, we are able to create reliability block diagram for quite complicated systems if we would just follow that combination of the standard diagram, you know, I'm talking about that diagram, what we saw, that cyclic one. Define the system, break down into reasonable subsystems, and then, if necessary, repeat the progress. Plus, top-down decomposition method. So that means if I have rough RBD at the first level of the composition, then I will go into every subsystem on that and consider the structure behind in order to get more and more details. Now, finally, if you have the detailed RBD, what we can do, or what we have to do, better to say, because the RBD alone is not our final destination, not our final target. For that given detailed RBD, we should provide the appropriate logical expressions for failure and survival functions. And now, guys, please keep in mind, in this case, it's absolutely necessary then you created rough RBD first, because that would help you a lot. Because by means of the appropriate rough RBD, you can easily recognize the necessary minimal cut sets. And having minimal cut sets, you will easily create the expression for failure logic. First, rough one based on the rough RBD, and then detailed. If you follow that approach, it's always easy game. And once you have the detailed logical expression for your failure logic, you will easily create the appropriate expression for the survival logic. You got my point? Any questions? All right, right now you're on exercise. Forget 0.0. It's yes.
I have a question.
Yes.
When we do when we negate a function or an OR, it converts to an AND, or it stays the same?
Probably you wouldn't believe, but yes, because I hope you remember the appropriate De Morgan transformation rules. So this is first one. If I have A or B all negated, that would be converted into A negated and B negated. And the same story, if you have A and B all negated, it will be converted into A negated or B negated. This is okay. what we did in the previous class, one of the first exercises.
Yeah, okay, thank you very much.
Okay, just keep in mind the Morgan transformation rules. Any other questions? Okay, then exercise. Again, forget 0. It's too trivial. We don't have time for it. Now, that one and that one. Guys, I'm expecting that you will complete these two exercises in the next 10 minutes, because here I'm asking you to give me an example of a technical system with a, let's say, technical system with serial structure. Now, please think about the previous classes. Could you please give me an example of a technical system, technical installation with a serial structure? Do you have any immediate example? Come on, guys, it's nothing else but a steam power plant. Think about that previous exercise. Steam power plant. Here, example of a technical system with a parallel structure. Any ideas? What should be used there?
Combined power plant.
Brilliant answer. So combined cycle power plant. All right, so use these two and define the appropriate RBD, define survival and failure logic for the entire system. Here, the same game. Define the RBD, define the survival and failure logic for the entire system, okay? Let's say 15 minutes maximum, then we have to start the discussion, please. Start working. So I will mute myself. If you have any questions, then please raise your hand, okay? Hold on. That's a good point. It's a good point. So now let us take a look. How you simplified that expression for the failure logic?
I think I'm a little like this. It will be 4, like 4.
Exactly. So now it's fine because you are about to describe the failure logic, right?
Yes.
Okay. So now how to simplify that expression?
Well, we put
because your previous version, if you would simplify it, would be result in not A and not B.
Okay.
So now, if you would simplify it, what's the common part? A negated is a common part, right?
Yeah.
So it would be A negated and 1 or B negated.
Okay. Then sería A negated 1 or
B negated.
yes.
All right. So what's inside of the bracket? 1 or something. What's the result?
2. 1 or
It's yeah. It's always 1, right? We can easily get the proof of that just by means of the table of truth.
Yeah. Okay.
So 1 or something is always 1 because 1 or 0 is 1. 1 or 1 is 1, right? So from that point of view, that expression would be reduced to A negated only.
Okay.
And think about the previous exercise. We've got exactly the same result for that structure, but by means of the table of truth and KV diagram. We've got exactly the same result.
Okay. Yes.
You agree with me?
Yeah. I totally agree.
All right, guys, what's your result? Do you have any other result? Should we discuss some other solutions? Then let me ask the question, was it clear enough or something was not 100% clear?
I think it was clear.
All right, then let me share my screen again. Now we're in the point number 3. So what do we need? You have to consider 2 out of 3 redundancy. First, provide rough RBD for that structure. And please think about your homework. Actually, if you complete your homework, then you already should have some partial results. So anyway, 2 out of 3 redundancy. Create first rough RBD. And then for that rough RBD, you have to create survival and failure logic. Okay, rough RBD, and then for that rough RBD, you have to create survival and failure logic. Any questions? If this is not the case, then please start working.
A negated or B negated. And then for the success condition, we just negated all of that. And we came with the answer B and C or A and C or A and B.
Okay, so let me check the first expression. So B negated or C negated? Yes, agree. And A negated or C negated. So also here, understood. Okay, got it. Seriously, I'm very surprised by that expression for failure logic. Could you please explain to me how you got it?
Yes.
Because seriously, it's not so obvious from the diagram.
Yeah, because we have 3 redundant lines. So for the system to fail, the 3 of them must fail. So for each one to fail, it's the negation of. Yes.
Understood. Understood. So actually what you did, you just considered 3 lines, and every line will fail. By example, the first one, if the component B is failed or component C. The second one will fail if component A or component C. And finally, the last one will fail if component A or component B is failed, right? Absolutely. Absolutely agree with you. But now, if I would say that this failure logic, can you right now add some? This is electronic form, not some screenshot, right?
Well, yeah, this is a screenshot because it's
damn it.
for us to present.
Then okay. I got your point. No problem. Then I would propose let me share my screen right now.
Okay.
Because I want to show you something. So let me just leave that stuff and create some just new slide in order to use that space. And I will start the presentation mode. So, okay, first, what I will do, I would recreate that rough RBD. The first, second, first, third, second, third. So it's quite inaccurate, but I hope you understood what I'm talking about. Here is the rough RBD for the 2 out of 3. This is not 2.003, it's 2 out of 3, okay? So, all right, you defined the failure logic as, So you defined as the first line should fail, and that could happen by means of first failed or second, damn it, second failed, and second line should fail, and that would happen if first one is failed or third is failed, and the last line should fail, and that would happen if second or third is failed, right? That was your expression. So if I would say now, the same failure logic could be expressed by means of first and second, or first and third. I hope you remember, if there's nothing between, then I mean and between the single variables. Is that true?
What are you asking, if they're the same?
Yes, actually, my question is, could you please give me proof that that expression and oh man,
It's not the same.
It's not the same.
I have the second one and I don't think they are the same.
Yes, I have the second one also.
That's interesting. So that means, again, guys, right now it's necessary to get a proof that that expression here and that expression here are the same. How to do that?
With the truth table?
Brilliant answer. So please provide a table of truth, and by means of that, we'll get the proof that these two expressions are absolutely the same.
Okay, I see they're the same.
Do you have the result?
Yes. I mean, I have the truth
Share
table
your
here.
screen, please.
Let me just... They're basically the same. You just gotta negate this. Oh. They're basically the same. I mean... But what I don't get is... when I was doing it, like how... I mean, you said that this was a failure, basically.
Okay, so that result, what you have right now, was obtained for the survival function, isn't it?
Yes, this was for the survival, yes.
But now, if you take a look into that table of truth, then obviously that table already contains the result for a failure function as well. Because every zero position means a failure. When we are about to provide the appropriate expression for the failure function, then we should take into account zeros, but not provide the appropriate CNF. We have to provide DNF. It's confusing, I understand, but all right, maybe let me share my screen again. And first, what I want to show you is just the appropriate script. I'm just opening. All right. And let me reshare my screen again. So guys, you see my script right now, right?
Yes, we do.
Yes.
Actually, this is exactly the same script like you have it. And here in that chapter, we have the necessary information about formal logic and how to deal with that. And by example here, I considered that situation with the gray code. It was the questions before. Why, if I have more variables inside of the KV diagram, why should we use that alternated sequence of the binary combination, not 0, 0, 0, 1, 1, 0, 1, 1, but we have to change it to 0, 0, 0, 1, 1, 1, 1, 0. So everything explained here. Besides, in that chapter, I also considered the situation with that 2 out of 3. Take a look. with the appropriate survival and failure function. Plus, I focus here on that situation in which typically one of the term would be that typical error in which we took into account also the combination of all of the three components. Make no sense. We already talked about it. It's that situation here. If you provide the appropriate rough RBD and you will take also that combination into account, make absolutely no sense. That line number 4 will be permanently failed, because it doesn't matter which one of the components will fail, first, second, and third. That line is permanently affected. From that point of view, that would be correct WBT. Guys, please read the script, is important. So now back to that situation. So here we go. What we can do, we can easily create right now the appropriate table of truth, right? What has happened to my PowerPoint? If I try to draw something, then it would be distorted in some horrible way. So what I'm talking about, first, how many combinations do we have? Obviously 8, right? You agree with me?
Yes.
2 to the power of 3. So, all right, now what we can do, we can easily create the appropriate results for failure and survival functions. In your previous result, you presented to me the table of truth for survival function. Let's do exactly the same way. So that means here survival function is 0, 0, 0, 1, 0, 1, 1, 1. You agree with me?
Yes.
As a consequence, for the failure function, obviously everywhere when I have 0 for survival, I will get 1 for failure. Quite clear, right?
Yes.
Yes.
Okay, brilliant. So now take a look. What I will do, I will just construct the appropriate KV diagram. So KV, and I will take it this way, 1 and 2. And here I will get component number 3. You can maybe have some other solution. It doesn't matter in this case. So I hope you remember in this case, we have to apply the gray code. So, oh man, it's annoying, seriously. Eu odeio essas situações. So then 1, 1 and 1, 0. I hope I'm correct now with that gray code. And here we have 0 and 1, okay? We should still have 8 results, and we have it, believe it or not. So, all right, if I'm about to express survival function by means of that diagram, what should be taken into account? I have to operate over that column here, and obviously for triple zeros, I have 0. 0, 0, 1, I have still 0. Then 0, 1, 0, 0, 1, 0, this is that combination here. It's 0. Then 0, 1, 1. So 0, 1, 1. Here I have 1, 1. So triple 1, 1, 1, 0, 0, 0, and 1, 0, 1, 1. You agree with me?
Yes.
Yes.
All right, then let me take a look. I will change now the color just in order to make it a bit better readable. What I can get with that diagram, I can define 3 groups. Well, all right, guys, I wouldn't change the color every time. This is my second and this is my third group. Okay, agree with me?
Yes.
That means the appropriate survival function could be expressed in this way. So I will take that first group. What is it? 1 and 2. 1 and 2, because 1, 1, and here component number 3 changes the value. Or what about that group? So here first changes, it would be second and third. And finally, for that group, 1 doesn't, second changes, so 1 and 3. Okay? Clear so far? Now, what I will do right now, I will create a KV diagram for the failure logic. The same principles. So here I have 1, 2, here I have 3. With all of the necessary combinations like 0, 0, 0, 1, 1, 1, and 1, 0. So and here I have 0, 1. But again, don't be confused. Right now we are talking about failure functions, so we are talking about that column here. Okay? So that means for all zeros, I have 1. Then 0, 0, 1, I have 1 because it's failure. So 1, 0, 0, 1. 0, 1, 1, it should be 0. So that means system operational. 1, 1, 0, 0. And 1, 1, 1, 0. So now for 1, 0, 0, 1 and 1, 0, 1, 0. If you take a look on that diagram here and that diagram here, what I can say is something obvious for you. Guys, take a look. That diagram here, where the hell's my mouse? Here we go. So that
opposite.
Exactly, that information is already given. So here in that diagram, I just replaced all of the zeros by ones. Here, I've got exactly the same position. Because here I'm talking about survival function, and here I'm talking about failure function. This is the only difference. So that means a shortcut. But okay, let me just create the appropriate logical expression for the failure function now. Okay, I'm talking about failure function now. What are the groups? Here, the first one, the second one. Oh, that's horrible. Isso é muito horrível. So right again. This is that second. And finally, that group here as well. Okay. So that means what should be taken into account? If I focus on that combination, the first one, keep the value, second changes, third keep the value. So that means failure of 1 and failure of 3. I'm working over ones. I'm about to create the DNF, obviously, right? So, all right, second group is, by example, that one. So what I have first and second. So failure of first and failure of second. And finally, the third group is that one. That means first changes the value, second kept, third kept. So failure of second and failure of third. You see that? Any questions about that? That's important.
No.
Okay, so if I would now operate over, let me now change the color, over zeros here. So I will define that group, that one, and that one. I'm still inside of the appropriate failure logic. Now I will operate over zeros. I will create DNF, right? You follow me?
Yes, you will create DNF, yes.
Okay, so that means what will be the expression, by example, for that first group? So first and second, both of them equal 1, so I should negate them, right? So that means first negated or second negated. And the second group, by example, is that one. So that means first changes the values, second doesn't, third doesn't. Equal 1, so that means should be taken negated into account. And finally, last group, this is that one. So what I have here, second changes, first no, and third no. So that means first negated or third negated. You see that? This is one and the same function here and here. Just that one is DNF and that one is CNF. This is the only difference. But I still have the expression for the failure logic. And now, guys, don't be confused. I know it's maybe a bit confusing at the beginning, but again, instead to make that all of that steps somehow separately, what I will do, I will take that table here for the survival function, but I will now operate over zeros to create a logical expression for the failure function. I will operate over zeros. Let me change again the color. So the same story, I will define the groups like this, that one, and finally that one. Again, I will operate over zeros, but I will create DNF, okay? Because here's just a negation of the survival function. Don't be confused by that. This is nothing else but a shortcut. So again, I'm operating over zeros, but I will create DNF, not CNF. So what I will get for the first group is quite obvious. First and second zeros, so that means negation of first and negation of second. So this is the next group here. Negation of first, negation of third. And finally, that group here. So that one. What is it? First changes the value, negation of second, negation of third. Take a look, that result and that result, what I've got from that dedicated table of truth that I constructed for. This is nothing else but somehow shortcut, okay? Once you created the table of truth for the survival function, it's not necessary to create some additional column or to have some dedicated table of truth for this failure function. You can obtain the appropriate expressions directly from that KV diagram. But if you are not 100% sure, then just create additional column and then you can construct the appropriate KV diagram. You will get all of the necessary results in DNF, like we had it here, or CNF, like we got it here. Most important stuff, we got now the proof that that expression here and that expression here are absolutely the same. Don't be confused by that. Any questions?
No. Yes, I have a question.
Yes, please.
Can we say if, for example, I mean, if we have like the survival function, can we say that the failure function would be the same, just negated?
Of course.
Or is
of
just
course.
a coincidence in this case?
No,
Okay.
no. It's always the same story. So that means survival function is negation of the failure function and vice versa. Failure function is nothing else but negation of the survival. Let's get a proof. So if I have that result here for the survival, here, I have that result here. So now I can say failure function is nothing else but negation of survival. So that means one and second, I have to remove some stuff here because otherwise I have no space. So remove all of that and maybe a bit more accurate. So take a look. So again, I've got that result here for the survival. Now I want to create the appropriate expression for the failure logic. I can just say failure is equal negation of the survival. So that means I have to take the expression for survival function as I have it here and apply the negation to the entire expression. What I will get? Nothing else but 1 and 2 all negated, and because of the De Morgan transformation, I hope you remember, 2 and 3 all negated, and 1 and 3 all negated. That means now I have to apply again the De Morgan transformation on that term. What I will get? Now I have to use the brackets, because otherwise it would be a wrong result. First negated or second negated, and second negated or third negated, and first negated or third negated. Compare it with that expression here. You will see it's exactly the same. Can you see it?
Yes.
You agree with me? This is that exactly the same result.
Yes.
Okay, guys, any questions about that?
I don't think so.
No, all's clear, thanks.
All right. Then let me jump back. I think we are in the last exercise. Let me check the time. Okay, we're good in time. So what's necessary right now? We're in the exercise number 4. We have that bridge structure consists of the 5 elements. What I have to do, I have to provide the table of truth, and we have to provide the KV diagram for failure and survival function. And then, of course, we need the appropriate expressions for failure and survival function. What I would strictly recommend, use some spreadsheet like Excel, by example, or some Google stuff, just in order to have a better organization of the table, because you can imagine you have to take into account 2 to the power of 5. That would be amount of the rows in the table, okay? It's not some trivial one. You got my point? Start working, please. Interesting. So, all right, first question. Did you read the script?
Well, part of.
Part of. Okay, brilliant. So let me take a look. We have the bridge structure. Yes, I can see the assignment in the The table of truth, you provided 2 columns for survival and failure function independently, right? So that means that Carnot diagram below, is it done for failure or survival function? This is not 100% clear for me.
This will be for failure.
For failure function. So that means 1 is failure, right?
Yes.
Understood. Yeah, totally agree, but let me check the situation with the gray code. So for 3 and 4 is done correctly. Could you please explain to me how you got the gray code for the components 1, 2, and 3?
1, 2, and 3.
Yes, because in this case we have 8 combinations and we have to know how to construct the appropriate gray code. We know how to do it for 2 variables, but how to make it for 3?
Well, I follow the structure that you said before, that we just need to verify that one of them changes. So
okay.
so for example, here, the only one that changes was this one. And I was verifying that only one of the
All right, quite complicated approach. Let me present some, let's say, good pattern how to create the gray code for, let's say, it doesn't matter how many components. Let me just briefly share my screen and then we'll proceed with your solution.
Okay.
So, all right. You see my screen right now, right?
Yes.
Yes.
So let's say we have the component 1, 2, and 3 with appropriate binary combinations. So first, what I will do right now, I will create the gray code for components 2 and 3 only. That means 0, 0, 0, 1, 1, 1, and 1, 0. Okay? What I will do right now, I just will mirror that result to the second half. That means 1, 0, 1, 1, 0, 1, and 0, 0. You see that? I just mirrored. So what should be done now? For the first variable, I have just zeros in the first half and all ones in the second. Do I have the same result?
Yes, I have the same result.
So that's the way how it could be done, because otherwise I should really find somehow all of the combinations and positions of all of the binary combinations in order that I have just one jump, by example, from that position to that one, from that to that one, etc., and then finally even to that one. Okay, you got it. So then please reshare your screen again. All right, so now the next question is how to build the groups. Could you explain it, please? Okay. Is that the biggest possible?
No.
No, exactly. And for the red one, the same story. It's not the biggest possible. Just take a look. You can change exactly. Much more better. Yes. And then. All right, maybe actually I've got a very nice result. What I see from the, let me share my screen again. Just in order to save our time a bit and accelerate. And let me change to the script. I will zoom in a bit. So take a look. Here we have exactly that exercise. You see my screen right now, right?
Yes.
Yes.
Okay. So here we have that bridge structure. Now, if you think about the beginning of the class, we said that the appropriate failure logic could be expressed by means of the appropriate minimal cut sets. So in this case, I can define the minimal cut set number 1 as a failure of 1 and failure of 2. Minimal cut set number 2 as a combination failure of 1 and failure of 3 and failure of 5. So that cut set. Minimal cut set number 3, combination of failure of 2 and failure of 3 and failure of 4. So that means another one. And minimal cut set number 4, failure of 4 and failure of 5. So these two are failed. Now, very important is, if I would create the appropriate table of truth and then the Carnot diagram for the failure function. So here I'm talking specifically about the failure function. What I will get, this is my KV diagram for the failure function, and how to get a gray code for 3 variables I explained already. I hope it's clear. How to get the gray code for 2 variables we already know. So now, by means of that KV diagram, I can define the appropriate groups. I will working over ones to create disjunctive normal, hope it's better. So I will create first that group here, because it's rectangular, and I have 8 ones inside, so power of 2. Everything is fulfilled. Then I will create the red group, which is that here. Again, 8 inside, rectangular, everything is good. Now, orange group, which contains these 2 ones and these 2 ones. I scroll the KV map by means of that connection here. So that one and that one. 4 ones inside, rectangular, good. Now, to tell the truth, the trick in for that specific case is how to build the green group. Because the green group are nothing else but that corner elements of the first half. Okay, that would be the group number 4. I can tell you there is another way to work with Carnot diagrams, just in order to, let's say, simplify it, but for me it's not a simplification. For me it's vice versa, that make the stuff even more complicated. Take a look. If I would fix that variable now, that means the first one, I can split the entire KV diagram in 2, because here I will fix the value of 1 by 0, and because of that I will get just the first half. And in another case I will have just constant 1 for the first variable. I will get the second half. I prefer to have that unified form. You had just to know the corners should be taken into account as well, in the upper half and the lower half in the same way. Some questions?
I didn't know, like, the green ones, that it could be possible. I thought that the only way that to do it was like if the...
Yes. This is what I said. It's an art how to work with KV diagrams. You have to know it. Again, just in order to focus on it again, if you split that table here, and you will assume that you have to operate with 2 tables or 2 KV diagrams instead of 1, you should just know the corners should be taken into account as well. So this is the so-called scrolling. All right. So having that situation for the blue group, what we can say? What is that value of the blue group? First constant 0, second constant 0, third changes the value, and 4, 5 changes the value as well. So that means the value of the first group would be nothing else but first failed and second failed. You follow me? Is that clear enough? Okay, for the red group, what we have for the red group? Immediate answer, first, second, and third changes the value because that group contains everything, right? That means we have to take into account just 4 negated and 5 negated. This is the value for the red group. What about the orange group here? 4 negated, a constant value. 5 changed the value. All right, so 4 negated should be taken into account. Now, 2, 3, 2, 3. First changes the value. So that means for the orange group, we'll have a combination 2 negated and 3 negated and 4 negated. And now for the corner, what do we have for the corner? First, keep the value. Second, changes. Third, keep the value. And what about that? So what do we have here? The fifth, right? So that means 1 negated and 3 negated and 5 negated. Now take a look. Here we have the definition of the minimal cut sets as we done it, let's say, analytically, right? We've got not 1 and not 2, or 1 is failed and 2 is failed. And where we have that result here, this is exactly the blue group. You see that? Then minimal cut set number 2, as we define it analytically from that structure here or from the appropriate, a diagram. So minimal cut set number 2 is defined like failure of 1 and failure of 3 and failure of 5. And this is exactly the green group as we discussed it a few seconds ago. Minimal cut set number 3, failure of 2 and failure of 3 and failure of 4. This is nothing else but the orange group here. And finally, minimal cut set number 4, failure of 5 and failure of 4. So what is that? This is the red group. So that means, guys, if you have the appropriate table of truth, if you create the appropriate KV diagrams, by example, for the failure function, then you will obtain the definition of the minimal cut sets immediately from the KV diagram. The KV diagram will generate for you all of the minimal cut sets automatically.
But you can also obtain it by just looking at the RBD, right? Yes.
Correct. No discussion about it. But now imagine instead of 5 elements, you have 15. Can you clearly define the appropriate minimal cut sets?
No.
It's not so easy, right? So that means the complexity will be growing and growing rapidly if you have more and more components inside. Of course, and no discussion about it, that the complexity of the appropriate KV diagrams would be even, let's say, will grow even faster. But there is a lot of the appropriate software which allows you to create and, let's say, calculate the appropriate KV diagrams with some reasonably higher degree of complexity. Right now, of course, we are talking about quite simple examples, quite simple structures. And because of that, also the structures of the KV diagrams are quite simple. But nevertheless, my intention is to give you understanding that from the RBD using the table of truth, because by the table of truth, we don't think, we just consider all of the possible binary combinations and the results, right? The table of truth could be generated automatically. I will present to you that way in the digital failure diagnosis. We will work with that, and you will see how trivial that task could be solved. So that means once you have the appropriate table of truth, and if you have some way to convert the table of truth into the KV diagram, then the definition of the minimal cut sets would be done automatically. You will receive minimal and necessary expression for a failure logic. That's the very important point. And again, I have to focus on it, minimal and necessary, because the next topic, what we're talking about, are failure and survival trees. And you will see that it's an absolute necessary step to minimize your logical expression before you construct the appropriate structure of the tree. Is that clear so far?
Yes.
Any questions about that exercise, guys?
No, I think it's the same result, but in a different way. Could I show you?
Yes, present your screen, please.
Can you see it?
Ah, very interesting.
I put the
If I understood correctly, no, man, I have no idea. Could you please explain how you got that result here?
yes, well, this is the color. It's white, but you cannot see that well. It's 1, 2, 3, 4, and 5.
Okay.
And well, this is my table of truth.
This is the table of truth. Okay. And what is in the column F? What is that?
Just white, like the output.
All right.
And then I did it the other way around. Instead of having 3 variables in this side, I just put A and B. And I got this table, which is, well, this diagram, which is a lot different than Ricardo's. And down, I just copied this one and pasted it, I think, 4 times to represent the groups. For example, this is one group. Then these 2 should be another one. Then another one here. And the yellow one should be this one, for example. Just so they didn't overlap.
I'm just totally confused by that split.
Okay.
That partial results, because right now you have 5 partial tables, if I understood correctly.
4. I think this is the main one.
This is the main one. Okay, all right, yes. Got it. Hold on. So okay. What are the dimensions? This is 4. It should be 4 by 8, isn't it? Top we have just that main table, right?
Yeah.
So now, more specifically, what are the tables below?
They were just for me to represent like the overlapping. Like, for example, this one was meant to go here, but then this color, I didn't know how to put it.
All right, damn, it's a complicated approach, seriously.
Yeah, I mean, I did it on paper and it was easier, but when I did it in Excel.
But the only question is, what's your result right now? Do you have the same result or not?
Yes, I think it was 1, 2 negated.
So it should be 1 negated and 2 negated.
Oh, yes.
Not 1, 2 negated.
Okay, yeah, it was 1 negated.
Because it's a huge difference between these two. So yeah, 1 negated and 2 negated, or
4 negated and 5 negated. Or 1 negated and 3 negated and 5 negated.
Probably yes, it depends. Okay, that could be all right.
And 2 negated, 3 negated, and 4 negated.
Okay, that could be true. So you have 1 negated and 2 negated, 4 negated and 5 negated, 1 negated and 3 negated and 5 negated, right?
Yes.
2 negated and 3 negated and 4 negated. That's correct. That's correct.
Okay. Thanks.
So, all right, guys, any questions about that exercise?
No.
I think not, but I just have a comment to Fernando. Probably, it's different because you did the KB diagram according to the survival logic.
Yes.
I made it with the failure logic. That's why it looks a little bit different.
Okay, maybe this is the case, right? Okay.
Yes, it is. Now I can see it. Yes.
All right. So good, guys. Any questions? Because this is one of the essential tasks, and everyone should understand why we did it this way, and more specifically, how to apply the techniques on different structures. What we'll get later in the class. Because again, the main idea of the minimal cut sets. Of course, if possible, to define the minimal cut sets by means of just analytical analysis of the appropriate RBD. That technique will allow you to define the failure logic by means of the minimal cut sets first, and then you have to understand the structure behind of every minimal cut set. By means of that two steps approach, first rough expression for the failure logic, and then detailed expression of the failure logic, you can easily define also the survival logic. That would be just a negation of the failure, okay? So now, with the last exercise, I also presented to you the way how to define the appropriate minimal and necessary logical expression from the table of truth directly. And you saw that the result, how it was defined by means of the minimal cut sets and how it was defined by means of that approach from the table of truth and the KV diagram, delivered absolutely identical result. That's very important. So again, any questions about that material? Because we have to make the next step. And I hope you remember we agreed to have half an hour more. We will start the next topic right now. Let me share my screen.
Teacher, I just have another question.
Yes.
Can I show you let me show you.
Yes, please share your screen.
Okay. For example, the approach that you said that it was easier to get this table. For example, if instead of 5, I have 6. Should I put it like here?
Then
or would you recommend?
Yes. I would recommend to define a 3 by 3 in this case.
Okay, and do the same approach as mirroring the first two columns.
Exactly that way.
Okay, perfect. Thank you very much.
You're welcome. So, all right, any other questions, guys? Okay, if this is not the case, then right now we have to make the next step. So that means we are able to create reliability block diagram. We are able to define the minimal cut sets and create the logical expression for failure and then survival logic based on the minimal cut sets. But now we have to calculate the numbers somehow, because you remember, for us, it's necessary to understand the values of the RAMs: reliability, availability, maintainability, and safety separately, but nevertheless, it's still necessary. So for all of that 4 parameters, we have to generate the appropriate numbers. In other words, our target is to calculate probability that the system will be operational or will fail at some specific time point or within some specific time interval. I already used the essential words. I said probabilities and how to combine the calculus of the probability with appropriate logical formulas. Because what we have right now, we have just some formulas to describe survival or failure logic. In order to be able to calculate the values, we need to get acquainted with the next technique. We have to understand the method of the fault tree analysis, or in generally event tree analysis, because we can construct the appropriate tree structure either for failure or survival logic. Now, take a look. We already discussed the technological or electrical plan for the LC circuit, right? If you take a look on these two constructions here, what is your feeling? Which one is correct for that given technological plan? The first one or the second one? I know I'm a bit ugly because I didn't explain by example what is the meaning of that gate, right? This is nothing else but OR. And this is nothing else but AND.
The second one is the representation.
So you mean that one is correct, right?
Yes.
So now the answer is quite simple. It depends. Because first you have to understand the structure of the tree. Take a look at that example here. We have here some circles. That circle or bubble and that circle or bubble. This is nothing else but basic event. In this case, the basic event, what could it be? Component failed, component operational. So from that point of view, if I'm about here to describe, by example, that my system is operational, so I would make a top event here. This is the top event, some final result. And I would define, all right, I'm talking about survival logic. Then that diagram would be wrong because here, let me create the RBD first. Inductivity, capacitor. This is my RBD, right? I hope you remember this is the correct RBD. So if I will try to describe by means of that tree structure the appropriate survival logic, that means my system is operational if inductivity is operational or capacitor is operational, which is obviously wrong, right? But if I would define now the top event here, not survival, but failure, then actually that tree structure would be okay, with one exception. To be more precise, I have to mark that top event, basic event here as failure of inductivity, failure of capacitor. In this case, that tree structure would describe the failure logic absolutely correctly. The entire system will fail if inductivity is failed or capacitor is failed. You see that?
Yes.
And here for that structure, we have that brilliant situation in which we can say, all right, that structure is nothing else but survival function of the entire system. So the entire system is operational if inductivity is operational, capacitor is operational. I will remove that 2 dashes just in order not to confuse you. So again, the entire system is operational, top event. survival logic, if inductivity is operational and capacitor is operational, and that reflects the appropriate RBD. So that means that tree structure is nothing else but survival logic as it's given by, by the RBD. And that tree structure is nothing else but the appropriate failure logic for that given RBD. Okay, you got that point. So that means later on, we will extend or enhance that structure, the tree structures, with appropriate numbers, with the probabilities, by example. Here we will get the appropriate probability that the inductivity is failed, and here we will get the probability that capacitor is failed. And by means of the appropriate rules of calculation, we will get a final result here for the probability that the entire system is failed, and vice versa. If we will get 1 minus the probability that the capacitor will be operational, 1 minus y that capacitor will be operational, we will get also here some result, and the entire system will be operational. Okay, that's the guideline. Any questions so far? Seems to be not the case. Then the situation is quite trivial if we have to deal with some serial structure, by example, like this one. We already considered that situation. We can easily provide the appropriate logical expression for survival and failure function. So now we're about to construct the appropriate trees for survival and failure function. Again, guys, some similar task will be on the exam. And one of the typical issues or errors that the students do, they just not mark the top event. A top event should be marked unambiguously. Is that survival, so R function, or failure, so that means F function? You should define it. Besides, yes.
If we just put the R and the F, would that be marked okay?
It would be absolutely okay. If you mark it okay. R for the survival and F for the failure function, it's absolutely okay. So another important thing, if you're working with a tree, you should define also the basic events correctly. So that means if I'm talking about survival function, that I should use the variable names directly. And if I am about to describe the failure logic, I should use it negated. So I have to mark it like either not as, or I have to use that symbol here, okay? Just in order to unambiguously mark that basic events as failure of the appropriate components. You got that point?
Yes.
Again, it's very important. If you do that mistake on the exam, then unfortunately I have to reject the entire result because the tree structure is wrong. Easy like this. All right, if I have to deal with appropriate parallel structures, then I already told about it. You have to start with a failure logic first. So also here I have to mark the top event unambiguously. It's failure function. And I should use either a definition of the basic events this way or this way. So negation, okay? I would strictly recommend that you use that way to define the basic event. So name of the variable negated. Clear so far, right? Any questions?
Can you repeat?
So all right, here we have that RBD. two structures that are parallel, two subsystems or two components which are parallel to each other. So we have to deal with the redundant components, right? So the appropriate logical expression for the failure function is given here. So that means I will get failure if subsystem 1 is failed and subsystem 2 is failed, right? Now, that logical expression could be visualized by means of the appropriate tree structure. So what I will do, I will create first two basic events, the bubbles, and I will give a name for every event here, like S1 negated, because I'm talking about failure function, S2 negated. Then I have to use AND gate, because take a look here, I have the AND gate, to combine these two events to each other. And here I have my final result, my top event, failure of the entire function. You got it?
Yes, I got it. I just have a question regarding like all the FTAs. I mean, they are a graphical representation, right? But I don't like get how is this different from doing an RBD kind of.
Well, all right. The RBD represents survival function, right? Event trees could represent both of them, failure and survival. This is actually the only essential difference. Plus, and this is the usage of the appropriate trees, probably tomorrow, depends on your performance, we will start calculate the probabilities. And you will see how it would be possible having the probabilities for basic events, calculate the appropriate probability of the top event.
Okay.
Okay, that's the point. Any other questions? All right. Now, we talked today about the minimal cut sets, right? And how to define the appropriate failure logic by means of the minimal cut sets. The idea is quite clear and obvious. That approach could be also reflected by the appropriate tree structure. Well, the idea is brilliant, but there is some unobvious issues, and you have to be very careful about it. Because take a look. By example, we have the basic event failure of the component number 1 inside minimal cut set number 1 and inside minimal cut set number 2. You see this? The same story for failure of the component number 2 that appears inside of minimal cut set number 1, but also inside of minimal cut set number 3. And the same story for 4, 5, etc. Now, be very careful with that. The situation of the logical expression as we have it here is absolutely correct one. There is no problem with it. But if you would now try to construct the appropriate tree, take a look. What I did for that example, exactly for that example here, I will construct the appropriate failure tree. You see, the top event is the failure function. And what I did at the first level is nothing else but minimal cut set number 1 or minimal cut set number 2 or minimal cut set number 3 or minimal cut set number 4. I will just jump back. This is exactly that expression here. You see this? So far, so good. Everything is good. But now I have to go into every box here, because right now I have just some kind of proxy for the minimal cut set number 1. And I have to take into account the appropriate tree structure. And for the minimal cut set number 1, I will get this tree structure like this. Because I hope you remember, we said, all right, this is failure of 1 and failure of 2. Here, the same story for minimal cut set number 4. It's nothing else but failure of 4 and failure of 5. Now, the problem is, by example, here I have the situation failure of 1, failure of 3, failure of 5, failure of 4, failure of 2, failure of 3. So now take a look. I have here the basic event failure of 1, and here I have the basic event failure of 1. If I would now construct it this way, so to have some 2 independent basic events inside of that subtree and inside of that subtree, I will get a wrong result. Because from, let's say, physical point of view, that event here and that event here, let's mark it this way, is just one and the same event. This is just one and the same component. And because of that, to have a correct structure, I should, let me remove that unnecessary stuff. I should have that basic event only once and not twice. So right now I have twice, one and the same event. Instead, what I should do, I should take it just once into account. I will define it here, failure of 1, and I have to distribute it between that subtree and that subtree. In this case, my tree structure would be correct. The same story for that event and that one, that event and that one, and the 5 as well. Okay, the 3, of course, the same story because I have some multiple appearance here. Is that clear so far? So yes. Be very careful when you have some logical expression and you're trying to construct the appropriate tree structure. Be very careful not to duplicate the appropriate basic events. In order to correct the, in order to get the correct result, you have to take the appropriate basic events only once into account and then split between the multiple gates if necessary. You got my point?
Yes, I think so.
All right, that was some crash course into event trees. Now, let us skip that exercise because it's again boring one. Let's focus on that one. So you have to define a tree structure for survival and failure logic if you take into account 2 out of 3 redundancy, okay? So 2 out of 3 redundancy. First, provide rough RBD. Then provide failure logic, because we have that mixed structure, parallel and serial. What I would strictly recommend, define the minimal cut sets. First, a list of the minimal cut sets. Then define the appropriate failure logic, and then define the expression, logical expression for survival logic. And after it, we will proceed with the construction of the trees. You got my point. 3 steps. First, rough RBD, definition of the minimal cut sets, definition of the failure and survival logics, and the trees. For failure, where's my mouse? Here we go. For failure and survival logic. Okay, you got it. Any questions?
Not now.
So, all right, guys, we have just 12 minutes to work. I would say start working immediately. As soon as you have the result, let me know. Otherwise, consider it like your homework. We will continue tomorrow with that exercise, because it would be one of the key exercises. It's very important that we have a clear understanding of how to solve it. You got my point?
Yes, could you just repeat the things we had to make? The RBD, or the rough RBD, and
all right. Again, let me repeat. First, to solve that task, you have to create first rough RBD for 2 out of 3. We have to take into account 2 out of 3 redundancy. You have to create the RBD first, then you have to define a list of the minimal cut sets. And by means of the minimal cut sets, you have to define the failure logic. Once you have the failure logic, you can easily define also the survival logic. And now, if you have the logical expressions, the task would be to define the appropriate tree structure for survival and failure logic, okay?
Yes, thank you.
All right, then please start working now. I will mute the mic, but I'm still important today. Today we've got the first experience with a failure, or better to say, with event trees. We know now, hopefully, how to get from the appropriate RBD, reliability block diagram, or starting from the RBD, how to create the appropriate formal logical expressions for failure and survival logic. That could be done either by means of the appropriate table of truth and then KV diagram, or you can obtain the appropriate minimal cut sets. That means minimal and necessary combination of the failed components directly from the RBD, if you're just skilled enough and if the RBD is simple enough. By means of the minimal cut sets, you can provide the appropriate expression for failure logic, and then as a negation of the failure logic, you will get the logical expression for survival. And again, it would be minimal and necessary expression. What we are doing right now in that exercise, we just complete all of that steps. Because first, for the 2 out of 3 redundancy, you have to create an RBD. From the RBD, you will try to define the minimal cut sets. Or if this is not possible for you, you will create just the table of truth. You will create the KV diagram for failure and survival function, and you will obtain the appropriate minimal and necessary logical expressions. For that expressions, for the formulas, you will create the appropriate tree structures for failure and survival logic. I can tell you right now, try not to get into that typical trap, because as we saw in the previous example, if some of the basic events are appeared in multiple positions, at multiple positions inside of the logical expressions, it should be taken just once in the tree and then distributed accordingly, split it accordingly. Otherwise, you will get the wrong result. All right. So then, for tomorrow, first complete that exercise as a homework. We will start with the analysis of that exercise immediately at the beginning of the class tomorrow. Then, depends on your performance. For tomorrow, we should have a first touch with the probabilities and how the logical expressions are connected to the calculation of the probabilities. So that means how to calculate the probability based on the appropriate logical expression. That would be the main target for tomorrow. If you have no questions about the class today, then we can wrap up. Hope to see all of you tomorrow, the same time, same channel. We'll start 3 o'clock sharp. Any questions?